All right, here we go. Week 10, day 1. So we're going to be talking about the worksheets that we're due today. And after we go over them, maybe we'll give you guys another crack at them as well. Because this is the kind of stuff that will be on the midterm. Let's go take a look at a pipeline worksheet. And see if we can hide the student name. Download you. All right, so the main thing when you do pipelining is for the pipeline worksheet. Okay. There. Okay, so is to figure out the dependencies, and then you reorder to avoid read after write dependencies. Those are the bad ones. Other kinds of midterm already. Week 12. 2 more weeks. Yeah, you're fine. But there'll be, all this architecture stuff we've been talking about in addition to programming. Then after that, who knows when we'll do the final third of the class, because normally a third of this class is physical computing and wiring up Raspberry Pis and stuff like that. So maybe, I don't know, maybe I get the school to come by and pick up the Pis and we'll do projects for the last third. I don't know. Find out. Or we could do like all... I have some cool ideas for assembly programs as well. We are going to do... so you do have a homework assignment due this Friday. I think I made it Friday, not Thursday. Friday. And the assignment is doing sepia toning. I posted a C version of the program on Canvas. And you have to sepia tone your program. Let's see if I can find my implementation. I bet I sent it to Muia last night when he was asking me if my running time was a typo, which was one of the best compliments that I've gotten, because no, it's not a typo. That's literally how fast it runs. It will sepia tone a 4K image in 0.02 seconds. 0.026 seconds. So that's pretty fast, I think. Pretty fast on a fairly low-powered machine like this. So you see the Kyoto image has been successfully sepia toned. There's no integer overflows we can see here. Muia liked his artwork better. Let's see here. But you can see like there's some blue in there, So I agree it does look better. I agree it does look better, but it's not sepia toned exactly. It's kind of, yeah. There's still a little bit of green right there and a little bit of blue right there. Sepia toning removes that. And then Muia's partner, take this one, and you can see that the light, so it's a little bit different from mine. Here, let's see if I can put mine side by side. You can still see the details in this one on mine, on the sign here. And this one lost all that detail. So this one is technically wrong, but yeah. So this is saturated successfully. So you can see that the colors here were successfully saturated. They didn't overflow, but they did blow out to be all white. So you can see you've lost information here and here on the image. So just watch out for that. Okay. Do not lose the detail. See how there is text here on mine? Text here. Okay. And if you ever get the chance to go to Kyoto, highly recommend it. I don't think this year is the right year for traveling to Japan. They're still trying to have the Olympics happen, and so right now the plan by the Japanese government is to not allow any foreigners, so they're going to have an Olympics without any tourists. Which defeats the entire purpose of the Olympics, in my opinion, but yeah, it's going to happen. Stop trying to make fetch happen. It's going to happen. So yeah, so the Gion district in Kyoto has a bunch of traditional houses in it. Not all of Kyoto looks this way, but it is a absolutely gorgeous place to visit. This is the White River. It's not the only white river in Japan. There's a lot of them. Are there East Mountains in Japan? Yeah, I've been to at least 3 East Mountains, Higashiyamas, in Japan. Here's the White River again. Yeah, and so some tea houses here. The Gion district's a pretty cool area to visit in Kyoto. So if you get the opportunity, definitely go there. I skipped it the first time we went to Kyoto. Actually, we went to lots of other stuff. We went to the Fushimi Inari Shrine and stuff like that. But you've probably seen this before. Broad in Japan did a nice video on Kyoto recently. Cool. Yeah. I've seen most of his episodes. Fushimi Inari is the shrine that has all these vermilion archways like that. It's pretty fun. Students will race through the shrine. The thing being, like, if you can do the circuit within whatever time period, you get like an A on your next test. That's their belief. Torii Gates, yeah. And so all the words on them are the sponsors of that Torii Gate. Yeah. So kind of want to go this year. Probably not going to happen though. All right. Yeah. No, the shrines are a business deal. Okay. So make sure you guys do the sepia toning. Like I said, I have a bit of C code for you here on Canvas. So you have to write this in ARM32. You don't have to use neon. If neon still confuses you, you don't have to do it, but please just message me, because neon's not really that bad. It's the same assembly you've been doing all along. It just will do it on 16 chars at the same time, which is nice. It's really nice. Your darken filter on the previous assignment could have been 3 lines of code. You know what I mean? Like, load, shift right, store. And people that did that had a running time of like 0.01, 0.02 seconds, something like that. So they could have gotten 100 frames a second processing 4K video. It's pretty good. All right, so correctness is worth a C again. So those of you that did not care about your running time, got a C on it. Yeah, okay. With or without using neon. You use neon, you don't have to use neon. If it scares you, you don't have to. I would recommend using neon. Okay, so I did some benchmarks. I actually updated the times on the server because we are running on a faster Raspberry Pi server now. I didn't realize that. Well, I did realize it, but I didn't update the README file as aggressively. So for next year's class, you'll notice the times they have to beat are smaller. So it is a much tighter bound on the running time for next year's class. So yeah. So anyhow, for the sepia toning, I ran the code in C++. I ran the code in C++ with the optimizer turned on, -03. You might see some references to -04. -04 is occasionally used. I've seen it actually do something very rarely over the 20 some odd years I've been doing this professionally. -03 is pretty much the top level of optimization. -04 is sometimes used for experimental optimizations. So I tried it just to see if it made a difference in it, and it didn't. So in C++, running this code here took 1.58 seconds with the optimizer turned on. In assembly, my code took 0.025-ish. Okay. So, yeah, 40 frames a second. It's pretty good. You do sepia toning at 40 frames a second on a crappy Raspberry Pi. It's power of assembly. Okay. Are we doing this in your ASM image directory? Yeah, there's no new assignment for it. Just make a new .s file and have at it. One thing you might notice in this class, I'm kind of having you guys just like make your own Makefiles now, just because I don't want to hold your hands, the whole time. So so you can see in Mui's directory, he's got a sepia.s here, and then if you look at and so that's separate from student darken.s, right? And then if you look at his Makefile, you'll see that he's probably added a line to compile the .s file into a .o file, and to link together all of them. That's interesting. Okay. I would probably pick one or the other, but whatever, it's all good. And then his code is not defining student darken, so it's possible that he modified main.cc. Aha, if def student darken, elif sepia, else darken. I don't see any of the. Oh, there you go. D sepia. There it is. Yeah. So he's defining a compiler flag, a preprocessor flag, in the Makefile. So that tells, when you do -d, that tells the preprocessor there is a variable called sepia defined. What value does it have? Who knows? Who cares? It's defined. That's all we care about. And then inside of main.cc, you can say if def. So if sepia has been defined, then insert this line of code here. If student darken has been defined, insert that line of code there. Else do this, else do that. Okay. And so preprocessor is really useful for excising chunks of code and putting chunks of code in. You could probably do that with an if statement as well, but with the if statement, then the things would actually have to exist, right? So this is actually a nice technique. If there's like a function you haven't written yet, like if you just haven't done student darken yet, the code will actually compile without it, and it won't try, it won't even see that. The C++ compiler won't even see that line of code until you -d student darken. So this is a way that you can kind of get code in that doesn't exist yet, if that makes sense. Because this takes place prior to the compiler even running. C++ does not allow you to have a function call without actually having the function existing. You'll get a linker error. Okay. Probably shouldn't call it darken time here. I'd probably do something like this. And this is something that a few of you guys had trouble with, which was it didn't tell you if you were doing the student darken code or the reference darken code. So I would probably actually do this student sepia time. And then this would be the reference sepia time, or reference darken time. Okay. Saved. You're welcome, Muya. So, time to copy Muya's Makefile. Yeah, I mean, if you want. But the point is like, for these assignments, I'm like not just like handing them out to you like I did in CSI 41, because this is your last semester with me, and you've only got, like a few weeks left before you're out of here, and you need to know how to out of the nest, little bird, and fly. Yeah. So. Yeah, dude. There's this end of the year is coming up. End of your 4 semesters with me. Define a few weeks. Like I don't know. When's the end of the year? I don't know. But when some students get to other colleges, they sometimes have trouble because they've seen Makefile, but they haven't made one yet, and so out of the nest. So here is yes. So this is how I did it. So structure is this ASM image. So this is the last one, but this is how I did the Makefile. So you can define a variable in C++. You can define a variable in Makefiles that will define which C++ compiler you use. There we go. I said it correctly this time. So by setting CC, which is very common in these Makefiles, in fact, it might even be standard. That defines what the C++ compiler is, and so I'm using G++ as the C++ compiler. These are the options that I'm passing to the C++ compiler. You notice -C is not one of them because CC flags gets passed to the link step as well. And so the link step, I want to make sure that I have all these things turned on here. as well. There's like 8 weeks left. Yeah, sure. Theory. I'll get you guys ready. Don't worry. Or if you want, you can always fail the class and you can take it again. Okay. Just ask me. I'll fail you. It'll be great. Okay. Okay, so yeah, so what do I have here? So if you make a variable in a Makefile this way, ass is the assembler, yeah. Yeah, and so I put that in there because you guys are probably used to using G++ for everything, but there is actually an assembler. And the assembler is called as, whatever. And so, anyway, so if I wanted, I could recompile this code with clang, like that. And then what will happen, make clean, it will use clang instead of G++ for every line, except for the one with ass on it. Okay, so this is useful if you want to find out if one of the compilers is better than the other at doing this stuff, right? And sometimes it makes a big difference, right? Sometimes the compiler will see an optimization that the other one won't see, and it'll be dramatically different. Sometimes, nah. So the only downside is it will eat up 15 seconds of your life because compiling with cimage is slow as F. And then if we run this, 0.027 seconds. So that's pretty good. That's actually, I think, faster than G++. Make clean, make last 8. So if you want, you can put all 3 commands on one line like that. And so you can simply see, and so you don't have to go through every line of your Makefile and change G++ to clang and G++ to clang and G++ to clang. You do $ parentheses CC, and then it'll just use whatever variable you created there. It's very common in Makefiles to do that. And with CC flags, you can change what standard of C++ you're using, what optimization level you're using. I don't have debugging turned on. I've got all sorts of warnings turned on. You notice it's not warning because I don't like having any warnings in my code whatsoever. So it looks like clang ran in 0.031 seconds, and G++ ran in 0.031, and clang ran in 0.027. Let's run it a few more times. Give G++ 0.027, 0.029, okay, 0.03. Yeah, it looks like clang might be about 10% faster. Maybe. Okay. That's cool. Pro tip, switch out the compilers, see if it makes a difference. You can try different optimization levels. Yeah. All right, so basically I have it set up so that if I want to use the student darken, I uncomment that. But then it uses the assembly darken. And if I comment it, it uses the C++ darken. Right. The longer it compiles, the better, more break time. Using cimage, let me just give an entire TED talk while this compiles. Yeah, that's why when I refactored the code for CSI 40, I had the main.cc separate from your image. I used to have your image processing function in main.cc, so it'd be 15 or 20 seconds every time you recompiled your image filter. But what I did this last semester was I split it into 2 separate files so that your image filter is in one.cc file and main.cc is another. That's the one that includes cimage. Your thing doesn't know anything about cimage. I actually strip all of the cimage stuff out and I just pass a pointer. In fact, let me show you what that looks like because it's kind of cool. There's a whole, and what that does, it makes your compiles much faster, right? So if you go into CD image processing on the old server, and if you look at the Makefile, ooh, the Makefile is cool. So let's, I guess, go over that. So it's using G++ version 10. You can also try that one if you like. G++ version 10. The default target is all. Got extra space there. So it's going to default to doing that, which it would anyway. These are the list of CC files it's going to compile. And so rather than having them all down in these long lists, I just have one canonical list of all the .cc files. And I don't even need to do that. I could actually wildcard that. So I could actually have a Makefile that would just get a list of all the .cc files in the directory and compile them together, which is kind of cool. So like that. So if you use this as your Makefile, it'll just compile all of the .cc files. It creates a target for each .cc file that has the same name but .o instead. So if you have a file called main.cc, it creates a target called main.o. If you have a file called bug.cc, it creates a file called bug.o. And so you don't have to make all those different rules for all the different Makefiles. It will just grab all of the .cc files in the current directory and compile them to a .o version. And that's the rule on how it does that there. So for every .o file, it will compile a .cc file. It's dependent upon a .cc file with the same name. And it's also dependent upon this header file that is used, shared globally among all the files. And then that, it will use G++ using these flags here. -c, -c goes from a .cc file to a .o file. And that is the name of the file here. So this is a really cool Makefile here that will just automatically compile any C++ project. And then it goes from all the .object files to .a.out by saying G++, using all those things and optimizers, and that is all of the .object files, .o files. Okay. Yeah. Okay. So that is kind of my master Makefile right here. So that's what I use for most of my projects. You don't want to do that if you have CC files that are for different projects in the same folder, right? So if you've got main1.cc and main2.cc and they're different programs, you can't do this, right? This is for a one folder project. Okay. So anyhow, so on that other thing, it compiles main.cc and then it passes a pointer to the student code, and this is go back into that. So the students only see a 3D vector being passed to them. They don't see anything related to CImage here. All they see is they get a 3D vector. So I've stripped out all of the CImage stuff. And so that means that you can compile your image filter without any dependency on CImage up here, which speeds up the compilation time dramatically. So if we were to make this, you can see that main is going to take forever. Plenty of time to drink coffee. Because CImage is like 100,000 lines of code when it really shouldn't be. I've actually wanted to make a tool that would go through CImage and just find which chunks of code I was calling and strip out everything else. Because there's a lot of CImage that I will literally never use. So. Okay. What's wrong? Okay. All right, so you can see compiling main took forever, but now let's say that I've updated filter1.cc. So if I say touch filter1.cc, what that does is that updates the timestamp on it. So it makes it look as if I've edited the file. This is a very important tool if you guys are working with Makefiles, because sometimes you'll update your Makefile and then you go to hit make and it's like it's up to date. And you're like, no, it's not, because I need to recompile it. So you either do make clean if you want to rebuild the entire project, or you touch a file and then it will rebuild that file. So if I type make now, maybe I should. One of the downsides to touch is that if you give a wrong name, it actually creates a file. So touch does two things. It updates the timestamp on a file, and it also creates a file if one doesn't exist. So I'll actually touch a file sometimes to just make a file that I know I'm going to need later. Okay, so touch filter1.cc. There we go. Make. And you can see that's the compile time now. So rather than 20 seconds per compile, it's as fast as that. If I try typing make again, nothing will happen. But if I edit the file, 1,000, 2, 1,000, done, right? So this is one of the reasons why we have Makefiles. It speeds up compilation. And what you can do is you can isolate slow to compile files into their own thing and then have a function call to your code that you're actively working on. It's a very common technique used to optimize compile times. All right, so any questions about that? Any questions about Makefiles? Stuff like that? You're going to need to make it for Sepia Toning. Okay. Is there a manual on Makefile? Yeah. Sort of no, not you. The classic book is this one. GNU Make. This is the boss book on Make. You should be aware though that the industry as a whole is moving to something called CMake. Makefile is still very commonly used though. I like it better than working with CMake myself. So, and so it's got it's basically everything you need to know about Make is this thing here. And is it available? Yeah. Yeah, so when you go off to a 4-year, you'll kind of need to know how to do this. So, portable Makefiles. Let's see. Is the whole thing available? That'd be kind of cool. It's cool. Yeah, so I don't know if that's the whole thing or just parts of it, but there's that, and then there's Makefile tutorial. And so this website's pretty good as well. And so CMake is kind of becoming the industry standard for C++. But CMake makes Makefiles, and so it's not like you're exactly getting away from Makefiles, you know what I mean? You still kind of need to know them. But they do, yeah, it's probably worth learning CMake as well. Okay, have we worked with Git before, GitHub before? Has anyone here not used GitHub before? All right. This class hasn't? Not for class? Okay. So, yeah, probably not for the summer assignment. Maybe the next one we'll do a thing on Git, because that's also industry standard these days. Git is not the world's best source code manager, but GitHub, I'm sure you guys have seen GitHub and Stack Overflow. They're kind of like the two biggest tools in a... Oh, look, you can spin that. That's cool. You can spin the logo. It's amazing. Ah, never seen that before. Okay, so yeah, GitHub is sort of industry standard place to put your code repositories and stuff like that. Oh, you can even click on it. That's incredible. All right. Wallet Wasabi. All right. All right. What is Wallet Wasabi? Open source, non-custodial, privacy-focused Bitcoin wallet for desktop. All right. Okay, cool. And so if you want to get the source code for Wallet Wasabi, you can clone it. You can download the zip file, or you grab the URL here, and then you go onto the server and type wget the not wget, git clone, sorry. You clone it, and then it will download a full copy of that repository from GitHub. And so what you can do if you're working with your partner, and we'll probably do this, is you sort of you work on your code and then you push it over to GitHub, and then they pull a copy of it, and you can synchronize your work that way. And yeah, you've heard of Stack Overflow before? 3D rendering on a web browser? Yeah. It's actually been around for a really long time. Since the late 90s, they had something called VRML or something like that. A VRML. Didn't work very well, but they've 3D rendering in browsers has been a thing for actually a really long time. So you see it's downloading. Anyway, it doesn't matter. I'm going to cancel this. cd up, remove.rfww. We'll go over that next time. All right, so we need to talk about pipelines. Do you guys have any questions about Sepia Toning? The source code for it is right here. You need to translate the source code into assembly. Okay. I have. You deleted your whole CSI41 archive using Git. Yeah, that's what I mean. Like Git is actually not the best source code management out there. Pretty much every person I know that uses Git professionally has shot themselves in the foot at some point using it. Honestly, I prefer Mercurial to Git. That's it. Everybody uses Git these days, so it's like, all right, well, I guess we'll learn Git. So, any questions about Sepia Toning? You take the red value at the current pixel, multiply it by 0.393, add it to the green value times 0.769, add it to the blue value times 0.189. I'm saving the result here into a 16-bit number, because if you look, these numbers can actually overflow. These things add up over 1. So probably that person whose code I was looking at probably did a saturating add, which was causing it to saturate up at over, this value would go over 1, right? So, I'm saturating as well. Who knows? Please delete this comment. Do you need to create your own filters for this assignment? What do you mean? Like, yeah, you have to translate this into assembly. That's the assignment. You have to here's the C++ code. You have to do it in assembly, and you'll be judged. We'll do custom filters next time. For this one, it's just Sepia. But one thing that I think Mui and the other guy didn't notice was you actually have to Sepia tone both Kyoto and another image. Ribera, yeah. It's funny. Yeah, so you have to upload both Kyoto Sepia tone, so I can compare it against mine and see if you did it right. And then you also have to Sepia tone some other image of your choice and upload that as well. Okay. All right. Yeah, run it 3 times. Take the best time. Go. It's an all red Sepia tone. Okay, enough about that. Let's talk about pipelines. So pipelines are how you boost the throughput of a CPU. We're doing a 3-stage pipeline, which is sometimes used, most... I did actually see, I can't remember which one has a 3-stage pipeline. It came out fairly recently. But most, I should say most modern architectures have more than 3 stages. Okay. So when an instruction enters a pipeline, it completes on the 3rd cycle and none of the results are available before then. In other words, if you have add R3, R2, R9 on cycle 4, then the new value will not appear in R3 until the start of cycle 7. Any instructions that read from registers 3 will have to wait until at least cycle 7 to begin executing. So this is a puzzle, right? If no instructions can run, the pipeline fills with no ops, and you want to minimize those. So the first thing you do is you trace the dependency of the arrows, and it looks like he broke the formatting here. Um, so if you have a read after write, then that's bad. You have to have a 3-cycle delay in between. A write after write or write after read means you can't reorder above it. Okay. So read after writes point upwards, and the other two point downwards. Read after reads are fine. They're not really a dependency. Okay. So let's go through this. Add R0, R0, R1. What's going on here? Let's ignore that. The formatting is all screwed up. Let's look at this one. Okay, add R0, R0, R1. So we're writing to R0 here, and we're reading from R0 here. So we have an upwards facing arrow here. And so this would cause a pipeline stall, right? Because you have to have a 3-cycle 1, 2, 3, 4. So we would need to move this instruction down 1 in order to minimize stalls, right? So that the upwards facing arrows are bad guys that we're trying to minimize. Then we've got R3 here and a read after write here. Should be fine. It's 3 cycles afterwards. Let's see, R4. So we have a read after write here. So we need to move this guy down as much as possible. R6, R1, R8, R1. Okay. And so let's look at the reordering here. Oof. Okay. R3, R4, R5. So that instruction is moving up here. And then the, interesting. See, I would probably move this one up as well because this R4 is dependent upon this one. So we need to get this guy up as far as possible as well. So this one's writing to R3, R0, R1, R2. So he reordered it above. R8, R9, R10. So this guy is dependent upon no one. So yeah, sure, we can slam that in there. Get a free instruction out of it, basically. And then R2, R2, R3. 1, 2, 3. So instruction 1, 2, 3, 4. Yeah, it should be fine, I guess. So this guy is reading that guy, so there's no delay there. Cool. 0, 1, 2, 3. That one's fine. Add R1, R1, R0. That's fine as well. R6, R4, R7. So there is a 1-cycle penalty here, right? Because this R4 is being read here. So I would probably move this guy up 1. So I can move that guy up 1 so that we could not have a delay on that one. Okay. So that's so if you guys want to redo your pipeline instructions, go for it. The main rule is raw is war. Wait, no, that's WWF. What the main rule is you need to move things around. It's a puzzle. Computers do this automatically, but if you've got R0, R1, R2, and then these are all adds. I'm not going to write add. So the add doesn't matter. Unless we're doing a load or multiply, I guess. But I didn't add that in. So this is a upwards arrow because this is a read after write. And so what we have is if this just ran normally, there'd be 2 no ops in here. It'd be no op is what would happen. Okay. And so that's bad. So we would be running not very efficiently. So what we essentially have are 2 slots in between these 2 instructions where we can stick other instructions in. So if we have a command like R10, 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 like cool, that doesn't depend on anything else. We'll just shove that guy into the first slot here. And if we have another one that is like maybe a write after read, R2, 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 D2. Wait, no. It's a Star Wars joke. We can't move this one above here, right? Because this This would change the value of R2 for this instruction. So this would be a write after read. That's a downwards facing arrow. But so that stops us from being able to put the instruction above here. Right? When you have a downwards facing arrow, it blocks you from moving it up any higher than that, because then the value of R2 would change when this one executed. But what we can do instead is note that, well, there's that second slot here, so we can just stuff that guy in there. The second slot, and there we go. Now we've got no pipeline stalls. Anyone get them right? I imagine some have multiple ways to organize the code. Yeah. Yeah, there's no one right answer to this. There's no one right answer. For example, rather than doing it this way, I could have had them go the opposite way, right? So I could have this guy take the second slot, this guy take the first slot. It doesn't matter, right? The main thing is not having these no ops. You guys understand? So this is a read after write. Raw is bad. Okay. So anytime you have a upwards facing arrow, there are 2 slots for instructions, and you want to try and fill those slots with instructions down below or up above. If the ones up above aren't dependent upon anything, then you can move them downwards, and which has the effect of moving that one upwards. Either way, you're trying to space out the commands. Okay. So you're trying to fill those slots however you can. Okay. You guys understand? And then the other worksheet we did was float, right? We did the float worksheet as well. So the float worksheet, I think we had a quiz on this as well. Quiz. See, this is useful because you can kind of click on the bits and see what the representation is. So if all the exponent bits are 1, you can have negative infinity, positive infinity. You did that too, Lowell. Use the same website. Cheaters, you're all cheating. Nah, it's what I use to make the quiz. But you still have to kind of understand what's going on. All right, what? Is this thing not sorted by data? Okay. It helps to verify you're doing it correctly. Yeah, exactly. So let's take the quiz. You didn't know it existed? You don't have to. You don't have to know anything about it. Like, it was all doable by hand. I just did it to verify my own math. So what kind of dependency is this? So this is a read after write. So this is that one. Okay, this is bad. Read after write is bad. What is negative 10.125 in IEEE 754 single precision floating point format? Give the result in hex. I don't know what the 10 is for. Probably. Okay, so let's decimal representation, negative 10.125. Let's see, do that. So yeah, it's this one. Mega Chad was correct. Yeah, in hex there is no M character, right? So if you guys ever watched the Spiffing Brit, he did a CK3 game with a Mega Chad of Italy, who he exploited the way the experience system works to get this incredible ruler. Okay, so so how do we go about doing this by hand, not cheating using the calculator? Because on the midterm you aren't going to be able to just use the calculator to get the answer. Okay, so let's take it one step at a time. So we are going to do negative 10.125. So what is the first thing? What is the first thing in a floating point number? Sign bit. And is a negative number 0 or is it 1? It's 1. Good. So the first bit of the 32 is 1. Okay. Now we need, so we can ignore that now. Now we're going to convert 10.125 into binary. Okay. So what is 10 in binary? That's what happens when you have a bunch of Russian calculus professors. 1010. All right. So 10 is 1010. What is 0.125? What fraction is 0.125? What fraction is that? What? 1 over what? 8. Okay. So that's the 1/2 bit, the 1/4 bit, 1/8 bit. So that is the number we have in binary. 1010.001. So now we move the decimal to the left 1, 2, 3 times. Okay. And so the number becomes 1.010001. And so the mantissa is everything except for the leading 1. The mantissa is therefore 0, 1, 0, 0, 0, 1, and then all zeros after. Okay. The exponent is 3, so we have 2 to the third, but we bias it. So what number do we bias it with? 127. So what is 127 in binary? Well, not 127. What is 130? What is 130 in binary? And they do this, the reason why you bias it is so that you don't have to have a 2's complement number in the exponent. They do that so that you can just do a straight comparison of exponents and see which one's bigger. And so what they do is if you have one that's like 1111 and the other one is 1110, then it knows this guy is bigger than this guy by doing a simple comparison, bit comparison. Whereas if you have 2's complement, 1000 is smaller than 011, right? And so this bias is there mostly just to make the life of the CPU designers easier, or the people making the FP for the Fresno Pacific University. All right, so 128's bit is set, 64's bit, 32's bit, 16's bit, 8's bit, 4's bit, 2's bit, 1's bit. Okay, and so that is our binary. 1 1 0 1 0 0 1. And if we snap this back up here, we see that we have successfully converted between a decimal number and IEEE 754. Okay. You guys have any questions about that? Pretty straightforward. Not exactly perfectly straightforward. 2's complement's a little bit easier, right? But any questions about it? So if you have it, whenever you have a 2's complement number, whatever the high bit is, remember, it just represents the negative of what it would normally be. That's it. 2's complement's pretty easy. Do you guys remember how to multiply a 2's complement number by -1? So this number here is -58, right? -64 plus, no wait, plus 6, yeah, -58. Do you guys know how to multiply that by -1? Get 58. Anyone? You forgot. That's what I thought. So we'll do that because that'll be on the midterm, maybe. Who knows? You flip all the bits and add 1. That's not a very good plus. So that would be 0 1 1 1 0 1 0. So that is 58, I think. Let's see, it's 48, 56, 58. Yeah. So in order to multiply a 2's complement number by -1, you flip all the bits and add 1. Good news is it's open midterm, so you can always pull up a bit calculator and do that. But you really should know the theory behind it. So what if I ask it in English? How do you multiply by -1? Okay, so yeah, so that is kind of a review of the worksheets. If you guys have any mistakes on those, double check your work using the float calculator. I'll give you guys till Thursday to resubmit them. Try to minimize those pipeline stalls though. Okay. Otherwise, you'll never make something as genius as the fast inverse square root. Ooh, let's talk about that today. All right. So, the fast inverse square root. Let's see, I think I have this in a presentation, don't I? Do I? Do I not? I have a worksheet for it. All right. Well, let's talk about the fast inverse square because we do have a worksheet for it. It's right here. Okay. So and here's actually some binary calculators you guys can use. Let's talk about the fast inverse square root. So what is an inverse square root? An inverse square root is this. So it's when you multiply by 1 over the square root of n. Inverse square root. So when would you do this? Well, if you guys have taken game development, which I highly recommend, this is used in normalizing a vector. So if you have a vector that is pointed at 2 in the x direction and 2 in the y direction, and you want to convert it to a unit vector is a vector of length 1, then what you have to do is you take the vector and you divide it by the length of the vector, and that will give you the normalized vector. Okay. And I actually don't know what the hat means, I'm just putting it there to look cool. So equals the normalized vector. Okay. And so in this case, it should be like, what, 0.707, 0.707, something like that. So how do you do that? So first of all, you take the length of the vector. So the length of the vector here is the Pythagorean theorem. So it'd be 2 squared plus 2 squared, square rooted, which gives you the square root of 8, which is 2.83. And so you take each of the components, so when you do vector divided by scalar, each of the components gets divided by the scalar. And so you would have 2 divided by 2.83 as the x, and 2 divided by 2.83 as the y. And that would be, why did I close the calculator? 2 divided by 2.83, 0.707. Okay. And so, inverse square root. Okay. So, right? So normalizing a vector is very, very common in computer graphics. A lot of algorithms work with normalized vectors. They work with vectors of length 1. And they break if you have a vector of length 2.83. Okay. Quake 3 algorithm. Nah, man, this has been around longer than Quake 3. Yeah. So the fast inverse square root is done as a way of approximating this using black magic. So it is one of the most incredibly awesome algorithms ever made. And the funny thing is, like, nobody really knows who made it, and you'll see in a second that it is literally invoking black magic in order to do it. Okay, but this is the justification. Do you guys understand? Like, so if you have a vector pointed to 2, the fast inverse square root is used to convert it into a normalized vector, a unit vector. Okay. All right. So how does it work? So we just learned IEEE 754, right? And so IEEE 754 has a sign bit and some exponent bits and a mantissa, right? And so sign bit could be 0, 1. You got your exponent, and the exponent is like, you know, some biased exponent, right? There's like it's a biased exponent, and the mantissa has the decimal, the decimals minus, the leading one isn't drawn and stuff like that. Okay, cool. So how does the fast inverse square root work? Zach has posted it up here, so that makes life easy. So how it works, nobody knows. Now let's go through. Okay, so if you're going to take the fast inverse square root of 8, let's say, then you've got a long I, float x2 and y that are uninitialized. 3/2 is set to 1.5 float. The f afterwards means float. You can also use lowercase f. It's a little more common. x2 is equal to the number divided by 2. So this will give us 8 will become 4. So far so good. x2 is equal to 4. Awesome. All right. Y is equal to the number. So y is equal to 8. Snap this over here. Should only just click. Keep track of it this way. x2 equals 4. Y is equal to 8. This is really tiny, isn't it? Make it bigger. There we go. Okay, now for the black magic. I is equal to dereference, convert to a long pointer, the address of y. Okay, so let's take this step by step. So the address of y is going to be some hex memory address that doesn't really matter, right? It's 0, 5, F, 7, 8, F, whatever. Some memory address, right? So that part there is getting the memory address of y. Y is just 8 right now. So it's getting the memory address, some address in RAM. It converts that pointer from a float pointer, right? Y is a float, so the address of y is a float pointer. So this is a casting operation. You guys remember casts? Probably never seen a cast like this before. So this is casting it from a float pointer to a long pointer. Okay. This kind of stuff is a little more. This is a little more common in C, in the C world, than it is in the C++ world. C++ is a very strongly typed language, so you have to do really weird stuff like this to coerce a pointer to not be a pointer to what its type is. So sorry, I've lost my voice doing all the sea shanties. So yeah, and then we dereference it. So we've got this memory address, and then we dereference this memory address. And so what is at that memory address? What is at that memory address? 8, right? 8. But we have 8 in IEEE 754 format. And we're saving this into an integer. This does not put the number 8 in integer. This does not make I equal to, 1000. Nope. It copies the bits. It copies the bits, essentially, from Y into I. And the way the optimizer works, it probably actually doesn't do a copy at all. This is purely syntactic sugar because the language is being heavily abused right now. So what's happening is that you're going to have an int that holds whatever 8 is in IEEE 754, which we could either do by hand, like we just did, or we can go to the IEEE calculator, and we're going to type in the number. That's a different one. The number is 8. Okay, so this number, is that 32 bits? Yes. So that number is being stored into I. So I now holds 0, 1. Here, let's just put in hex to make it easier. So I now holds 41 0 0 0 0 0 0. Okay. And what is that in integer world? Does it matter? Probably not. So let's go to a binary calculator. Okay. Did you not do anything? Thanks. So this is 1,090,519,040. Okay. All we're really doing here, though, is just copying the bits from a float into an integer. The actual number of the integer doesn't matter. Okay. Then we naturally will take I and say I is equal to 0x5f 375 9df minus I right shifted one time. I think we don't need to explain why that is. So after we do that, I'll leave that as an exercise to the reader. Yeah, no, that is the point at which you go, what? Yeah. So we have taken a floating point number, converted it, just taken its bits and stuffed it into an integer, and then done integer subtraction with this magic number of all magic numbers here. We take the number, though, we shift all the bits to the right one. So this 41 is going to turn into, would that be 2? And then that would be a 0, and then we'll have an 8. And so we're going to take 5f375 9df and subtract out 20801234, which will give us what? Huh? What? Yeah, exactly. So that'll give us 3e5759df as the answer. We convert it back into a float. We take these bits and convert it back into a float. All right. So the hex representation here is 0x3e5. There's a pretty good chance I did the math wrong because I'm laughing so hard. df, and you can see that the decimal representation is now 0.2. Okay. So snap you. Yep. So then we take x2, which is 4. 4 times 8 times 8. 64 times 4 is 128, if I'm doing the math right. No, I'm not doing it right. 256. So it is going to be equal to 256 times 0.2. Let's see here. 4 times 8 times 8 is 256. So we have 0.2 times, no, 0.2 minus, oh no, it's 1.5. Okay. Oh no, y is not 8 anymore. Never mind. Y is 0.2. Okay, so it's going to be okay, so it's going to be 4 times is it 0.21 times 0.21. So 3 halves minus 1.5. Okay, so times nope. So we got 1.326 in here. So that part there is 1.326. Times it by 0.21, and we end up with 0.27. Okay, and so 2 divided by 0.27 is what we're looking for. So there you go. So there is your inverse square root. You guys all got that? Cool. Yeah, you can't write shift to float, right? So what he's doing is he's using the bits, and it doesn't even make a different register. It just will do a right shift on the register. It's because the C++ language doesn't allow this kind of monstrosity. Okay. Yeah. So this is one of the most famous algorithms of all time, and nobody knows who made it. They know it probably came out of SGI somewhere. People have investigated this. SGI is Silicon Graphics. It was the company that did basically all of the 3D anything, like back in the days. They were the company that invented OpenGL. If you saw any movies in the 80s and 90s, the 3D graphics were made on one of these kinds of things here. I've used this before, actually. Onyx, I had one of these too. Pretty cool. Yeah, they were the fastest graphics of 1993. Yep. We had one. We used it for a military flight simulator. And went out of business. Why? NVIDIA. Right? So there's no reason to spend all this money on... I had one of these too. Yeah, it's cool. Not me personally. I use them at my places of business. But it had hardware accelerated 3D graphics back in the day. And OpenGL was their baby. And so Microsoft created DirectX as a competitor for OpenGL, which helped put Silicon Graphics out of business. But it's funny. First released in 91 and 92. Yeah. So Silicon Graphics is now defunct. They're no longer around because you don't need to spend $10,000 for a supercomputer anymore to do 3D graphics. You just spend $10,000 on a 3090 hardware. So, yeah. SGA timeline. Yeah. They're still around for a while. Yeah. They're around for a surprising amount of time. Yep. But they died. NVIDIA killed them. So, yeah. So this converts it takes the bits from a float, sticks them into an int, right shifts the bits by 1, which you can't do on a float, subtracts it from a magic number, converts it back into a float, and does a Newton's method iteration to approximate the square root. If you uncomment this, it'll do it again. It'll do another iteration of the Newton's method to get a more accurate result. And at the end of the day, you've got your inverse square root. And so you divide it, you divide out the number, and you've got a normalized vector. And so this was a lot faster than doing it the long way, right? Square root can be a very expensive operation. On modern systems, square root's probably in the 20 to 80 cycle cost range. On older systems, especially if you lack a floating point unit, like it could be really bad, right? So you're not expecting to know this for the final. What are you talking about? Yeah, this is the final. You just have to do this all in your head on the final. Actually, you're gonna have to make a new one. Make a better one that's more accurate and faster. Yeah, no, so if you guys don't understand what's happening here, that's fine. Like the person who wrote this code. This is John Carmack, by the way. I'm pretty sure these comments are by John Carmack. And John Carmack is a genius among men. Like, he is honestly one of the coolest dudes ever, one of the most awesome graphics programmers of all time. My one claim to fame is I traded a series of emails with him back in the day. I was working on a new supercomputer, and I noticed that he posted something about the supercomputer that I was working on. And I was one of 8 people in the world who was working on the Terra supercomputer at the time. And one of 8 students who was working on the Terra supercomputer at the time. And so I wrote to him, I'm like, hey, you made this blog post about this supercomputer. You want me to benchmark something for you? And he wrote back, he's like, yeah, He's like, it doesn't have a frame buffer, so, you're not going to be able to run Quake on it, but How about you know, the map compilation thing? I'm like, yeah, that's a great idea. And so in Quake, you pre-compute visibility in a world like if you're in this room, you know, I can't see out my backyard. And so these visibility computations could take quite a while. And so like on my PC at home, it would take like 20 hours to do a visibility computation for the world. On the Terra supercomputer, it was like, I don't know, 3 times faster. So it was, yeah. And he wrote back, yeah, it's disappointing, but about what I expected, you know. So that's my claim to fame. I've had an email chain with John Carmack. I've talked to Robin Walker too, Team Fortress Software, in real life, actually. Okay, so yeah, so this is yeah. So if it confuses John Carmack, don't worry about it confusing you. It is treating the bits. It's taking all the bits and IEEE 754. And think about how weird this is. Think about how weird this is. This means the sign bit is getting bit shifted into the exponent, and the last bit of the exponent is getting bit shifted into the mantissa, right? And then it's subtracting some bit pattern from that other bit pattern you have, converts it back into a float, and then multiplies that result squared times half the original number, subtracting out 3/2, which is hilarious because, like you said, they have a magic number for this, but not for 3/2, right? This ought to be like BS magic number, right? And then multiplying it by, you know, the result again, and that's the answer. So, yeah. Yep. Watch the vid poster, covers everything. Yeah. So the video will go into the theory as to why this actually works, but nobody really knows where that magic number came from. They just know that somebody at SGI invented it. And they probably reverse engineered it, right? Like they probably ran the math backwards and got the magic number from. If you do this algebra backwards, you can derive what this magic number needs to be. It's probably where that came from. Okay. So, yeah, this is one of the most iconic black magic algorithms of all time. There's others. I don't know if I want to explode your head too much. It's a mathematical constant. Yeah, I guess. Yeah. Is it used in the industry at all? Not so much these days, probably because graphics accelerators will do that kind of stuff for you. But you know, yeah, sure. Yeah, still around. So, yeah. Any questions about it? I'm sure you have a lot of questions about it. I don't know if I can answer them. Yeah, can you go over everything again? What level do you unlock this? You want me to explode your guys' minds with one more thing? Cool. So this is unrelated to floats, but it's one of the best hacks I've ever seen. Again, I don't really recommend you guys do this, but this will probably help you with your assembly coding for the rest of the semester. So let's say that you're going to be copying from one array to another, right? So you got a from array, you got a to array, okay, and so basically it's just going to be counting downwards. Remember how we tend to count downwards until it hits 0, right? So it's just going to be copying from an array. Sorry, it's just copying into a register. And so that register, if that register is something special in hardware, it might be outputting to the screen or something like that. Okay. So, so it's going to copy a int, let's say. It copies an int, it decrements count, checks to see if count is 0 or below. If it's 0 below, it quits. Otherwise, it jumps back up to the top and does it again. You guys understand? Like, if I needed to do this in assembly, it looks something like this. Top. There, let's see. Yeah, it's just called top. Thanks for capitalizing it. Make it bigger for you guys. So let's see. We're going to LDR into register 3, loading from register 1, loading from register 0 with write back. We are going to add, we got some counter that's in R2. R2 is going to have -1 added to it. We'll do an add and set. Branch if greater than or equal to 0. Let's see. Branch if greater than 0 to top. Okay. Pretty fast code, right? Pretty fast code. You guys understand? So it's going to read from an array. The array is held in R0. So add some notes to this if you want. R0 is input array. R2 is the bytes copy. R1 is the output register. So let's say that output register is magical, like it's going to be drawing to the screen or something like that. Like if you have specialized hardware, you'll do that. You'll write to some memory address, and then stuff will magically appear on the screen. Okay. So pretty fast array, pretty fast loop, right? Would you guys concur? Like we don't have to move the pointer. Assembly does it for us. We don't have to do a comparison. Comparisons are free. This is like about as fast as you can make it, right? Wrong. This is actually pretty slow. Wrong. All of you are wrong. It'd be much faster to do this. You guys see that? What? It's called loop unrolling. Okay, I think we've talked about this before, but this is called loop unrolling. I wasn't trying to have an opinion. When you ask if I concur, I was just trying to say I concur. Right? No, to be fair, like if you guys wrote that code, I'd be happy, right? And again, I'd have to look up the syntax for that because I don't use exclamation mark that often. Don't quote me on it. I know it works with neon code. Okay. Because we multiply the instructions per loop by 8 and divide the amount of loops by 8. Yeah, so before we had 3 instructions per load, right? So the way we were doing it before, we'd have to do a load and add a branch, a load and add a branch, a load and add a branch. Remember, branches can actually be quite expensive, right? If the branch predictor gets messed up, you can actually have a pipeline flush on it. Probably not in this case. I wouldn't be too worried about it. But still, you're doing 3 operations per operation, right? This way, we're doing 8 operations with an overhead cost of 10, right? So in 10 cycles, we're doing 8 operations. Before, we would do 24 operations. So this code here it takes us from 24 cycles to 10. Right, so this code here is actually 2.5 times faster than the code we had before. And it could actually be much faster if we had if we don't have register renaming, right? Because then you get a dependency of like between loops, you're constantly writing to R1, and so if you know there might be some false dependencies there. If the Raspberry Pi doesn't do register renaming, which I don't know if it does or not. And if you get a branch mispredict, you could get a pipeline flush. So possibly this could be as bad as like, 80 cycles, right? So it could be somewhere between 24 and 80 cycles. Right? So the problem is, the exclamation mark doesn't work with normal. Okay, fine, I'll just look it up. It does work with neon. There is something similar to that for ray axes. Okay. It would be... There you go. That's how to do it in normal assembly. Okay. Okay. So who knew that textbooks would be useful, huh? Yeah, it's actually optimized all those times in CSI 40. Yeah, if you did a fizz buzz without any loops, you're just doing loop unrolling, right? No ifs, no for loop. Why the for? Because we're loading 4 bytes, right? So LDR load is a 32-bit load, so that's going to load 32 bits from R0. Actually, it should be post, whatever, close enough. So it's going to miss the first element. So I think it's, I don't want to look at the textbook again. That's the general idea. So it's going to load from R0, and then +4, and then save that result into R0. LDRB, if it was LDRB, I would do 1 byte, right? This is in your textbook, which all of you should have. Okay. The actual textbook, not the side books. The Bruce Smith book is really good. It's really good. Okay, so this is loading 4 bytes, and then it moves the pointer 4 to the right. It might be, I don't know, look it up. I don't like having bad code out there. Well, we could actually just do this every time except for the first one. Okay. Yeah. So this would work for all of them except for the first one. So the way of doing it, if we're doing it like that, is like this. There we go. Okay. Like I said, I mostly do this with neon, so. Okay. So that will read from R0 into R1 and then advance R0 by 4 bytes. And so there we go. Now, what's the problem with this code? This code will not work 7/8 of the time, right? When is this code not going to work? No, R0, yeah, number of bytes. Good point. Good point. Okay. I did say bytes. I was intending that to be I, which was the counter. Is the counter. Good call. Good catch. So R2 is I. So if it's 10, you're going to copy 10 integers. Okay. So, yeah, good catch. So, is this code going to work if we have 10, if the array has 10 integers in it? Will this code work correctly? What do you guys think? What's the problem? we have 10 numbers. The first time through the loop, we copy 10 numbers from the array into R1. The pointer advances. Everything's working well. Subtract 8 off of I. I goes from 10 to 2. We then run through and copy the next 8. Okay. Sing, do you see what the problem is here? So the up till here on the second loop through, it'll be fine. And then after that, all of these are going to be accessing memory outside of the array. Man, do you see what the problem is here? So, one way that I solved it is to not worry about it. So, like for my image processing thing, one of the things that I did to make it fast was I just went out of bounds and just didn't care, like a boss. Sunglasses. So what I do is I just make sure the input array was padded, like a boss. Okay, but the trouble is if you're writing this to like some register, and that register is causing like an electron gun to draw things on the screen, you're going to be drawing zeros all of a sudden on the screen, so you can't really do that. But yeah, like I'll just make the array a multiple of 8 and call it a day. Then I don't have to worry about it. You know what I mean? Don't. You know, like I said for the Bridges Mountains assignment, you can just make the edges of the array like really tall, and start one in, and then the algorithm will never go out of bounds because it'll never choose to go up to a high point, and then you don't have to do any bounds checking. You know, it's actually a lot faster that way to just make the array a little bit bigger, and then not have to worry about all those if statements. Am I too high? Am I too low? Handle the special cases for having 2 neighbors, or if I'm in a corner, there's 1 neighbor, or, you know what I mean? Like, you can actually make your code much faster by just wasting a little bit of RAM, padding out the array, in this case, making it a multiple of 8, and then just not caring about it. But, so why are there black pixels in a line at the bottom right of my picture? Yep. Mm-hmm. If you look very closely at some of my image filters, there will be a little bit of corruption in the bottom right corner. And just nobody's ever noticed it. So what Duff's algorithm is a very clever way of handling that. So what he's got here is, let's see if I can find a better version of this. Okay. So, no, it's the same code. All right. Well. Okay, here we go. You guys understand what's happening here? So if count is invented by Tom Duff at Lucasfilm. So yeah, so the register that he's writing to is a serial port, probably. So every time he writes that register, like it's sending out data over a cable transmission. So if the count is 10, 10 plus 7 is 17, divided by 8 is what? Two. So it's going to do the loop twice, right? So switch, so n is equal to 2, so it's going to do the loop twice. Okay. Switch count modulus 8. So 10 modulus 8 is 2, right? And so what you have here is this inside of a switch statement. So it literally does not do the first time through. So what happens is 10 modulus 8 is 2. So it's going to jump down to case 2 here. It actually changes how C... This is... In CSI 40 last week, a student's like, I like switch statements. This is why I hate switch statements. They don't behave the way that you think they should behave. This do is actually inside of a case. So it actually has a loop control structure inside of a case. And it falls through from one of the cases to the other. Okay? So if it was case 0, in other words, if we picked, let's say 8, right? 8 plus 7 is 15, divided by 8 is 1, so one time we're going to do this. 8 modulus 8 is 0, so then it will come here and do a do while loop. If you have a multiple of 8, it will do this do while loop, just as if it was written like this, with all those case statements gone, because it falls through one case to the other. All right? So if you had 24, it would do this do while loop exactly 3 times, and it would copy 24 bytes from the array into the register. Now, what if we had 10? Then it will issue 2 of these commands first. So it will copy 2 numbers, and then it will come up here and do these over and over again until... So, because 10 has 2 extra instructions, what this does is it has 2 instructions first, and then it does multiples of 8 after that. Didn't even know that can compile. Exactly. It looks like it shouldn't. The cases are basically a way of being able to skip parts of the do while. Yeah, it's going to issue a number of extra copies equal to the remainder. So if you have a remainder of 5, it's going to issue 5 extra copies, and then it'll do multiples of 8. So it'll do 8 at a time, 8 at a time, 8 at a time. And, you know, if you have 4 left over, it does 4 more at the beginning. Okay. C's default fall-through in case statements is long been its most controversial single feature. Duff observed that this code forms some sort of argument in that debate, but I'm not sure whether it's for it or against it. The omission of the postfix ++ on 2 was intentional. It can be used to copy from one array to another. That's where I've seen it before. It's copying from one array to another. But the original was to copy into a magic I/O register. Like I said, sometimes you have a register that when you write values into it, it will do something cool. In this case, he's writing it to a serial port, apparently. But if you have the ++ there, then it would you could use that to copy from one array to another. And if the array wasn't a multiple of 8, then it will generate a couple extra instructions to handle the balance of it. So let's see if we can find his thing here. So I'll post this, and you guys can peruse that at your leisure. 1988. Yeah. So I 1984. Okay. So he sent this email to Usenet, which was how bulletin boards used to exist on the internet back in the day, back in the 80s. So disgusting, no? But it compiles and runs just fine. I feel a combination of pride and revulsion at this discovery. Many people have said the worst feature of C is that switches don't break automatically before each case label. This code forms some sort of argument and debate, but I'm not sure whether it's for or against. So, yeah. Yep, so this is, yeah, there you go. So it's loop unrolling. Okay. And so what it does is basically, once you have the remainder, it'll jump to like one of these lines, kind of, if you want to think of it that way. Okay, so that was 2 of the most cool / horrible things you guys are probably ever going to see in computer science. Duff's device and the fast inverse square root. What do you guys think? How does your brain feel after that? Treating a float as a bit pattern, doing a bit shift and a integer subtraction on a bit pattern, then converting it back to be a float. Is mush a feeling? Yeah. Yeah. So if you ever feel dumb, just remember John Carmack himself. Right. So I'll give you guys that as it feels like being used ballistics shell. Yeah. So the worksheet on this, because why just talk about it when you guys can do it? There is a worksheet on this, and so it'll work you through the process. So the first thing you need to do is solve it yourself normally using normal math. So for example, if you have x, y, z, x is 2, y is 0, z is 0, that's a vector pointing to the right down the x-axis. If you're going to normalize it, it should be a unit vector, and so it goes from being a 2, 0, 0 to 1, 0, 0. Right? And so the worksheet walks you through how normal people do it, right? And then it's going to walk you through the fast inverse square root. So let's go through some of that. All right, so what is the length of this vector? So what is the length of this vector? If you have a vector that is 2 to the right in the x direction, what's its length? You guys should be able to do this one in your head. We have swung from like incredibly difficult to incredibly easy. What is the length of a vector that is too long in the x direction? 2. Yeah. So yeah, the length of that is x squared plus y squared plus z squared. Well, sorry, we need to first step by step. So 2 squared plus 0 squared is 4. And then you take the square root of this is 2. Compute the inverse square root is 1 over 2. So 1 over this number, right? 1 over that number. Multiply each component of that by this. So 2 times 1/2 is 1, 0, 0. Okay. So that's how you do it by hand. Okay. Okay. Now we're going to do it with the fast inverse square root. So convert that number there to float in binary. So what is 4 in binary? Right. Number is just 4. So what is 4 in binary? No. Floating point binary. Not easy binary, hard binary. Okay, that would be 4080 000. Of course. Just did that in my head right now. Don't pay any attention to me typing numbers into the IEEE 754 floating point calculator. All right, so we're going to now right shift it by 1 bit. So that turns into 20400000. We're then going to subtract this number minus this number here. Okay. And so we can do this by hand, or we can do a hex calculator. Fine, you could convert it into binary. Okay. All right, so minus. Okay, so 5F37 59DF minus 040 1 2 3 4. If you want this in binary, it'll be 0 1 0 0 0 0 0 0 1 0 0 0 0 0 0 0 0 0 0 0 0 0 0 0 0 0 0 0. Okay. All right, so 5F3759DF minus 20400000 is, yeah, we can do this by hand. 5 minus 2 is 3. 3 minus 4, that's going to be a carry, so it's going to turn into an E. And then 13 minus 4 should be, let's see. Well, the calculator has it as F. Let's 5F3759DF minus 2040. I'm not lining that up right, am I? Two, 0, 4, 0, 0, 0, 0, 0. Okay. So 5 minus 2 is 3. We're going to carry the 1 off that, so that's an E. E, that's 13. 13 minus 4 by my estimation is 9. No, 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 no. It's a 16. You don't carry a 10. Carry a 16. So that's 19 minus 4 is F. Very good, very good. Okay. 759DF. Okay. F 759DF. Be careful if you do it by hand. When you carry a 1, you're not carrying 10, you're carrying 16. Okay, so now we convert this back into a float. So I'm going to come up into here and type in the hex representation of that. So it was 3EF 759DF. So that is 0.483. Multiply each component of U by this to get U hat. So 2 times 0.483 is 0.966. So the answer we get here is 0.96600. So, what do you guys think? Is it correct? 0.966 versus 100. Is it correct? .966 1. I mean, it's in the right ballpark, right? Yeah, this is why it's called a fast inverse square root. It's not supposed to be accurate. Fast inverse square root is fast inverse square root. And this didn't do the Newton's method approximation either. If we did that, then let's see, what would it be? Let's see. What would it be? So it would be y here. It's 0.483. So we did Newton's method to get closer. So we had an error of about 4%, right? And so what would that look like? If you had an error of 4% in your lighting calculations, that means each pixel, if you should have a red value of like 100, you'd have a red value of like 96. And that could be noticeable. What you actually end up seeing if you don't do the extra iterations to get more precision, you'll see shimmering in the world as some of the pixels are 4% higher, some of the pixels are 4% less, and the human eye is sensitive enough to actually pick that up. But the thing is, they kind of average out over time. Some will be higher, some will be lower, some will be spot on. And so as you walk around, you'll just see kind of like, it'll look like all the walls are a little bit shiny, or they got mica in them. And some pixels will reflect a little more light, and some will reflect a little less, you know? And so it's noticeable. You'll see noise, essentially, in the image. So let's see if we can approximate this. Let's see here, 0.483. Okay. So x divided by 2, let's see, the number there is 4. Okay, so 2 times 0.483 times 0.483 minus 1.5 times... Let's try this again. 2 times 0.483 times if I could type, it's hard to twist your body and type at the same time, actually. All right, 2 times 0.483 times 0.483 minus 1.5 times 0.483 is pretty close to 1/2, right? So times -1. So why does it not do that? It doesn't allow a -1 in there. It's just subtracting 1. Oh, it's nice. Plus 1 time there. I just need to click on times 1 negative. There we go. 0.499. So if we do one iteration of Newton's method, it goes from 0.483 to 0.499, which is pretty close. That's actually pretty close. That'll take the error from 4% to less than 1%, right? And that's probably not going to be noticeable. If we do the Newton's approximation again, then let's see, where were you? There. Then if we uncomment that and do it one more time, then we will have an even better answer probably. Let's see, so it'd be 2 times 0.499 times 0.499 minus 1.5 can't do that, times 0.499. So we get 0.4999999 times -1. 0.49999. Something like that, right? 4 9s. 9999997. Okay. So that is a very, very small error, and that won't even be noticeable, right? Because if you're rendering in 24-bit color, yeah, you're really not going to see 1 pixel difference in 10,000. Yeah. You can't sub. You have to use the plus minus button. Yeah, yeah. I'm used to calculators where you can do that. You can hit times -5. It'll switch the operation to minus if you do that in Windows calculator. Okay, so yeah, it'll go. So this is the answer you guys need to give. So that's pretty close, but still kind of error-y. But if you did one level of approximation, then it would be 0.499 times 2 is 0.998. So that's 0.02 error, and then if you did it with 2 times, then that is very, very small error. It's imperceptible error. 5 9s and a 4. So that's pretty damn close to the 1, and you're talking about still being radically faster than actually doing the square root, because this is yeah. So that's a multiply. The casting actually doesn't do anything. You can do the subtract and shift in 1 cycle, right? So that's 4 cycles to divide by 2. Oh, it's a floating point, so it's probably still around 4-ish. Floating point division is actually much more expensive than floating point multiplication. So, which you would think, it's weird because it's the reciprocal, right? But it's true. Floating point division is actually usually much, much slower than floating point multiplication. And so if because of accuracy issues, and so if you want, you can always take the reciprocal and multiply, and you will pick up some error that way. But if you need speed more than you need accuracy, go for it. Okay. So what's the percent increase in runtime for every iteration? That's what I'm trying to figure out right now, Shami. Good question. So how many cycles is this? Can I mark this up? Save image. Desktop. WTF. Nah. Fast inverse square root. Can I mark it up? Can I mark it up? Yes. Cool. Oh, I can't undo it. I cannot undo it. Yes. I can erase it though. All right. So that's a constant that doesn't cost any time. This one will stay as 4 cycles. Ew. Let's make it bright red. So that's 4 cycles. Yeah. Okay. Options they give you are not very good here. 4 cycles. Okay, fine. Y equals number. That's probably 0. That conversion 0. That's 1 cycle. There. That conversion is 0. Because all that is just getting around C's limitations. And then we got here a multiply, a subtraction, and a multiply. So with 0 iterations of Newton's method, it has a cost of 5 cycles. The default square root, again, is somewhere going to be in the order of 20 to 300 cycles. And so if you do the 0 iteration method, it's going to be between 4 and 60 times faster. If you do 1 iteration of Newton's method, then that will add in 4, 8. This subtraction could be fused in. So it'll be about 12 cycles. So it'll be about 17. And if you do 2 iterations, then that'll be about 29 cycles. Okay. Yeah, there may be a way of optimizing that, but I don't see it off the top of my head. So yeah, so that's your comparison. So if you did a normal square root, you're talking of a cost on that order. Also, sometimes you'll actually have different options for square root. So that's something the Jedi don't tell you necessarily, which is that you can lower or raise the stroke size. Yeah. So the Jedi wouldn't necessarily tell you this, but there are different square roots available. A lot of times, some are more precise, some of them are faster, and so see you. We're done here anyway. So it can be hard actually to get a number on these things here. That's kind of a ballpark. I've actually spent time reading through manuals, like trying to figure out exactly how much these things cost, and all I can give you guys is kind of a range. And so you can see with the fast inverse square root, you can make it very fast, and what was that, about 4% inaccurate. This one is still faster than a square root, and it is like 90, it's like, what was it, 0.01% error. And on this one, it's like 0.0001% error, right? And so it's a trade-off of accuracy and speed. And that's something that you will see a lot. Okay, so I've given you guys the fast inverse square root as your homework for Thursday. And then for Friday night, have Sepia Toning done. You can do this with a partner. So feel free to partner up with somebody, and just make sure you note who your partner is so the cheat checker doesn't pick you guys up as sharing code. Okay. That's it for today, guys. I'm sure you have questions about this. I can't answer them.